Ladies and gentlemen, we, Marianna, Lena, Yannick and Jakob, want to present our project Recycling Waste Aluminium into a Useful Chemical, potash alum. But first, let me start by giving you some background information. Beverage containers are increasingly composed of aluminium cans. In Austria, around 800 million cans are sold every year, and the Austrian company Red Bull, for example, sells around 7 billion cans per year worldwide. Though it is so commonly used, it has its disadvantages. The major source for the extraction is the ore bauxite, a mixture of different metallic oxides. Bauxite mines are systematically exploited. Then, aluminium is one of the most indestructible materials, and it takes around 200 years to decompose. Furthermore, the toxic alkaline byproduct red mud emerges. And lastly, the production is highly energy intensive. The electrolytic process runs at low voltage, but it needs more than 100,000 ampere.
Recycling aluminium uses 95% less energy than producing it from raw materials. Our idea, instead of recycling it into new metal cans, was to transform scrap aluminium into a new chemical compound, which is potassium alum, or short, potash alum. It's used for tanning and dyeing of fabrics, in cosmetics or as an astringent to stop bleeding, for water purification, or for growing crystals in science kits. But how can you convert aluminum metal into a salt? This reaction involves two major steps. The first is the oxidation of the metal. Aluminium is protected by a thin layer of aluminium oxide. Strong aqueous bases dissolve this oxide layer and then attack the metal, as you can see here. Hydrogen gas is also formed, which is very explosive. Here we demonstrate it. The second step is the formation of the salt potassium alum when strong sulfuric acid is added. The expected theoretical yield of potash alum when using 1 gram of aluminium is 17.5 grams.
Now we want to show you the procedure step by step. Using sandpaper, we scraped off any paint of the can. With scissors, we cut 1 gram of the aluminium can into small pieces to get a faster reaction later. Then we dissolved them in potassium hydroxide. To speed up the reaction, we heated the solution. Hydrogen gas was generated, which we carried away by the suction of the fume hood. The colorless mixture turned dark gray. The reaction was complete when the hydrogen evolution ceased. Then we filtered the hot mixture to remove any solid residue. The filter was clear. In the filter, we discovered pieces of plastic. Therefore, we knew that the inner side of the can was coated with a thin plastic layer. We analyzed the brown residue and detected iron ions.
To get a salt, we slowly and carefully added half-concentrated sulfuric acid to the cooled solution, which got hot again from the neutralization reaction. White aluminium hydroxide precipitated, which completely dissolved again after we added more sulfuric acid. Then we chilled the hot solution in an ice water bath to enable the crystallization of potash alum from the supersaturated solution. We induced crystallization by scratching the inner walls of the beaker with a glass rod. Then we filtered the crystals in a vacuum filtration apparatus, rinsed them in ethanol and let them dry. We synthesized 11.8 grams of potash alum, which represents 67% of the theoretical yield. Lastly, we wanted to know if our salt is suitable for growing crystals in science kits. Here you can see our results. If you have any questions about the project, please contact us.